Right, so we've covered Bernoulli distributions, which are kind of random variables which are really the 0, 1. Binomial distribution, which is when we sum up n 0, 1 random variables. We've covered geometric distribution, which is sort of how long we wait until the first success from a number of Bernoulli random variables. Okay. The next we're going to consider is something a little bit different, which is the idea of a Poisson distribution. Okay, and as I'll discuss in a minute, the Poisson distribution is sort of the idealized limit of a binomial distribution. Okay, so let's talk about Poisson. Okay, so not Poisson, but Poisson distribution. Okay, and as I'll discuss, and we'll kind of reason as well, the Poisson distribution arises, okay, when we count the number of successes of an unlikely event from a large population over so examples of this to kind of make this a little bit more concrete. So one where this comes up is, for example, nuclear decay. So here we imagine that there is a very large substance, say that can decay gamma rays or something like this, okay, and that occurs from any given atom. Okay, so let's suppose we look at this substance, put a Geiger counter next to it, and measure the number of decays that happen, say, over a given minute. Okay, there's a large number of atoms inside this substance. Okay, so a very large population, but over any given minute, there's a very small probability of each one giving a decay. Okay, another example would be in insurance. So an insurance company will have a large number of contracts, insurance contracts, okay, and then a small proportion of those will actually experience some sort of incident and make a claim, okay. And so again, there's a large population, okay, and each individual contract has a small chance of wanting to make a claim. Okay, and so we ask what's the distribution of the number of claims that is made over that large population. Again, that's something that's appropriate for a Poisson distribution to consider. And the other might be sort of calls on telephone calls. So early examples of the Poisson distribution being used were for telephony. You have a telephone cable, okay, and you want to count the number of times that people try to make phone calls over that cable. There's a large population of people within a town or a city who have telephones and can make a phone call, but at any given time it's unlikely that, you know, it's a relatively rare event that someone then goes up and picks their telephone call and makes a call at any given moment in time. Okay. That said, you know, these days maybe the distribution of that has changed, things we use our telephones so much now, but let's say, you know, 100 years ago that was a reasonable model. Okay, so what is this Poisson distribution anyway? So let's define it. So the Poisson distribution okay, so for a parameter lambda, greater than or equal to 0, the probability mass function, okay, which defines the distribution of a Poisson random variable. So the probability mass function of a Poisson random variable is given by P of k, which is equal to lambda to the power of k divided by k factorial times e to the minus lambda. Okay, and that's for k equal to 0, 1, 2, or indeed any number there from there on. Okay, and we write that the random variable x, if it has this distribution, is Poisson distributed with parameter lambda. I often write it just sort of PO. Different people have different notations for this. You can write just Poisson lambda as well. That's perfectly fine also. Okay, so let's collate together a few facts associated with Poisson random variables. Let me just find the appropriate, here we go, appropriate page. So we can calculate the mean and the variance of a Poisson random variable. Okay, so I'll say lemma. So if x is Poisson distributed, then we can calculate its mean and its variance. Then e of x is equal to lambda, okay, and the variance also of x is also equal to lambda. All right, so let's prove this. Okay. Also, before maybe I do that, I'll just mention one thing. So notice it seems like a little bit of a strange form here. It's not completely obvious that the sum of the probabilities here add up to 1, but notice this is really the probability of getting k is equal to lambda to the power of k divided by k factorial divided by e to the lambda. Okay, and you might note that e to the power of lambda has a Taylor expansion, which is sort of 1 plus lambda squared divided by 2 factorial plus lambda cubed divided by 3 factorial and so forth. Okay, so notice this is the probability of k is just picking up the kth term from this expansion. Okay, and so if we sum out all of the terms here, we're just going to sum out all the terms in this expansion and then thus get that the sum of the probabilities is equal to 1. Okay, it's this sort of calculation that we're going to use as well for calculating the expected value of Poisson random variable. Okay, right, so let's just do that. All right. Okay, so, well, the expected value of x is equal to the sum of k equals 0 to infinity, the value of the random variable times the probability of the probability mass function equaling k, right? Which then we know from the form given above is equal to k times lambda to the power of k divided by k factorial, okay, times e to the minus lambda. All right. Now notice this k factorial, the lead term from this is k, which cancels out with this k. All right. So just remember that k factorials is k times k minus 1 times k minus 2, so forth, all the way down to 1. Right? So that k here is going to cancel out with this k. Right? So what I arrive at is that this is equal to the sum of k equals 0 to infinity lambda to the power of k, which I'm just going to write as follows: lambda times lambda k minus 1. Okay. If I cancel out the lead term from here, I'm just going to end up with k minus 1 factorial times e to minus lambda. All right. And notice I should also be a little bit careful here when I've multiplied by k equals, when k equals 0, I don't pick up anything here, so I could just change this k equals 0 to k equals 1, and I can do the same without any loss, change this 0 into a 1 as well. Okay, since the first term here with 0 is 0. Alright, so now look what I've got here. I've essentially got all the terms, I'm summing out 1, and then lambda squared divided by 2 factorial, then lambda to the power 3 divided by 3 factorial. These are all the terms that I'm considering here, so I'm essentially working my way through all the terms in the Taylor expansion of e to the power of lambda. Right? So what I'm going to be left with is lambda times e to the lambda times e to the minus lambda. Okay, this lambda goes out here. This term summed up from k equals 1 to infinity is just e to the lambda, and I'm times by e to the minus lambda. So I'm left with lambda. All right. Okay. So that gives us the first answer here. We can also do the variance term. It's not too difficult either. Notice that I could consider e to the x times x minus 1 here. All right. And when I got to this stage, I wouldn't just cancel out one term, I could cancel out 2 terms. Okay? So I could do the same calculation, write this out. Okay? Well, let's just do it. I'll write it out. K equals 0 to infinity k minus 1 times all these probabilities, which is equal to lambda to the k divided by k minus 1, k minus 2, all the way to 1 times e to the minus lambda. Right? And again, I can just cancel out 2 terms. So I cancel this out with this out with this. Okay? And you can notice I can do this sum not from k equals 0, but from k equals 2 here. Right? Because the first 2 terms for k equals 1 and k equals 0 are going to give me a 0 here. Right? So then I'm going to be left with the same calculation here with lambda squared e to the lambda times e to the minus lambda, which is going to give me lambda squared. Right? So from this I can kind of move this around to give me the variance that I'm interested in. Okay? So remember that the variance of a random variable is e to the x squared minus e to the x all squared. Okay? Which then I can write as e to the x times x minus 1, okay, plus e to the x. Notice this together, this term is just the same as this, right? I've just added and taken away the expectation of x, okay, and then minus e to the x squared, right? Now I know from my calculations above that this guy is equal to lambda squared, this guy is equal to lambda, okay, from up here. This is then equal to lambda squared. So I basically got lambda squared plus lambda minus lambda squared, okay, which then is just going to give me lambda, right? So that's how we calculate the mean and the variance of the Poisson distribution. Okay, a bit like geometric, there's some tricks involved, but you know, it's not too bad, just sort of things cancelling out nicely. Right, but anyway, that's not sort of, doesn't really get to the heart of why we consider the Poisson distribution in the first place. Okay, so really, when we consider a Poisson distribution, it's because it's in some sense the limit of a binomial distribution. Right, so let's just discuss that quickly and do that as an example. So lemma and this is sort of how we go from a binomial distribution to a Poisson distribution. Okay. Now, many of the most useful probability distributions that one uses sort of come up as the limit of different other simpler distributions. So we can kind of think of like Bernoulli distributions and binomial distributions as sort of building blocks, and on top of those we can build more interesting probability distributions and more that have suitable levels of abstraction for the kinds of problems that we want to consider. Okay, and the Poisson distribution is a nice first example of this. Okay, and in a little bit we'll cover one called the normal distribution, which is probably more important maybe than a Poisson distribution, but is also an idealized limit of a binomial distribution. Okay, so anyway, consider a sequence of binomial distributions. Okay, or let's say binomial random variables. In particular, I'm going to let x superscript n be a binomial distribution over n experiments where the probability of success of any individual experiment is lambda divided by n, okay, where lambda is some positive number like before, okay, and I'm going to let x be a Poisson distribution with parameter lambda, okay. And what we're going to show that the probability that x to the n equals k as we let n get bigger and bigger and bigger up to infinity, that this is going to get closer and closer to the number of the probability mass distribution of a Poisson random variable. Okay, so what that's saying, just to interpret for a second, is if we've got a very large n, very large population, and the probability that any given member of that population has a success, okay, is quite small, and small means in proportion to the size of n, okay, that the probability that we get, say, k successes from that population gets closer and closer to a Poisson distribution, okay. So what we're thinking here is if we've got, say, 1 million people taking out insurance claims, taking out insurance policies, and if there's about a 1 in a million chance of any given person taking out, making a claim, then the number of claims that we're going to get in total is going to be approximately Poisson. Okay. So rather than working with a binomial distribution, okay, where n has to be specified, we can no longer need to specify that value of n and end up with a much simpler distribution to work with. All right, in particular Poisson distribution. Okay. So let's just go through the proof of that. All right. So, well, the probability that our binomial distribution is equal to k, as we know, is given by n choose k, okay, times the probability that we get k successes, which is lambda divided by k to the power of, lambda divided by n, sorry, to the power of k, right, times the probability of all the failures that we get. So 1 minus lambda divided by n to the power of n minus k. All right. And now, from way back, you might remember that we could write out sort of the expansion of a binomial distribution. Okay. So remember that n choose k, I'll write this on the side. Remember that n choose k is equal to n times n minus 1 times all the way down to n minus k plus 1 divided by k factorial. So k, well, just write k factorial for now. Okay, so basically pick up the first k terms, okay, from n, let's say n factorial. Okay, so what I'm going to do is I'm going to write it out like that, and I'm going to notice that I've got, rather than, what I'm going to do is I'm going to match that up with the sort of n to the power of k over here, right? So I'll write it down and you kind of see what I mean. So notice I can write this out as n times n minus 1 all the way down to n minus k plus 1, okay, so k terms here, divided by these k terms each equal to n, divided by n times n times n. Okay? And then finally I've got this k factorial left over. Right? And also I've got this lambda to the k as well. Right? So that's just a sort of slightly different way of rewriting all of these terms here. It's just a different way of writing it is like this. Okay? And then I'm going to split this piece up as well. I'm going to split it into two parts. Okay? So I can write this out as 1 minus lambda divided by n to the power of n, and then that's divided by 1 minus lambda divided by n to the power of k. Alright? Now, what I'm going to do is look at each of these terms, okay, as n gets really big, right? So let's just investigate that for a second. Well, the first is easy. N divided by n is going to cancel out here, so that doesn't matter too much. Well, let's have a look at this term, n minus 1 divided by n. Okay, so that's equal to 1 minus 1 over n. Okay, we can think about what happens to that as n gets really big. Well, as n really gets really big, this is going to get closer and closer to 1. So this is going to go to 1. All right. Similarly, if I go for the next term and the next term all the way up to this one, the last term I'm going to get is 1 minus k minus 1 divided by n. All right. So if I divide this by this, what's going to happen to that? Well, that's going to go to 1 as well. Okay. So as n gets larger and larger, there are k terms here, right, and every single one of them is going to get closer and closer to 1. Right? So what I'm going to expect out of these first k terms here is it's going to get closer and closer to 1 times 1 times 1 k times. Okay? Next, what about this term? Well, this term doesn't depend on n. So as n gets larger and larger, nothing's going to happen to this guy. Okay, so we're going to get lambda to the k divided by k factorial for this. All right? Now, let's look at this bottom term here. All right? It's kind of the same as what was happening over here. We've just got 1 minus lambda divided by n to the power of k. Right? As n gets larger and larger and larger, all right, we're just going to get something that's closer and closer to 1. So let's suppose like k is 3. So it's just going to eventually be like 1 cubed or something like this. Okay? So as n gets larger and larger, this term, okay, is going to get closer and closer to 1. So effectively dividing by 1 to the power of k here. All right? Okay, the last bit, all right, and I'll go into a bit more detail in a minute, but my claim, and I'll prove to you why this claim is true in a second, okay, is that this, as n gets larger and larger, is going to go to e to the minus lambda. All right, and I won't prove that to you quite yet, okay, but what we're going to get here is e to the minus lambda. So collecting this all together, we're going to get lambda to the power of k divided by k factorial times e to the minus lambda. Okay, which is exactly a Poisson random variable being equal to k as described above. Okay? Right. So this kind of, I'll explain this part in a second, but this sort of explains why the Poisson distribution arises. Okay? You've got a large number of independent experiments, okay, each of which has a small probability of success proportional to the size of the population. Okay, as we let that population get larger and larger, it gets closer and closer to a Poisson distribution. So rather than having to deal with all these strange combinatorial terms, okay, as we might with the binomial random variable, it becomes significantly simpler to work with this Poisson random variable instead. Okay. And so it's a good approximation of a binomial distribution for a large population, assuming under the assumption that the probability of success is small. Okay. In a minute we'll look at the same sort of limit, but where the probability of success is kind of moderate. Okay, and that's where the normal distribution is going to arise. Okay. Right, so it's one last thing, just to kind of tidy up, I'll explain why this is true. So this is really just a result from analysis that you should be taught probably in another course, but we'll cover it here as well. Okay, so I'll do that as a kind of separate claim at the bottom here. So the claim that's required for our proof is that 1 minus, I'll write it as x divided by n to the power of n goes to e to the minus x as n gets closer and closer to infinity. So as you let n get larger and larger, this is going to converge to e to the minus x. Okay, let's prove that. So what we can do is I can look at this and I can notice that I can take this to exponentials and then take logs again. All right, so this is the same as taking the exponential and then the logarithm of 1 minus x to the n to the power of n. Okay, so just logarithm is the inverse of the exponential and vice versa, so this is just going to give me back where I started from. Okay, another thing we know about logarithms is that powers come out at the front, so that is just the same as this. Alright, now let's have a think about what this is sort of saying. I can sort of rephrase this in a slightly different way. Okay, notice that I could in fact minus off from this the logarithm of 1 and then write it like this. Okay, and why might I want to do that? Well, we're sort of looking at the change in the logarithm from the value of 1 to the value of 1 minus x. And remember, the logarithm of 1 is 0, so it's not making any difference to this expression. Okay, now I'm going to change it a little bit more. Okay, I'm going to rewrite it as, notice this is the change from 1 to x divided by n. Okay, so there's a change of size x divided by n made over this expression. So why don't I divide by that relative change? Okay, so notice I can look at this as minus e to the x times the logarithm that I had on the top there divided by minus x divided by n. Okay, so all I've done is sort of times and divided by minus x divided by n here. All right. Now I'm going to draw a picture of what this is really doing. Okay. So over here I'm going to draw sort of my sort of z-axis, and then here I'm going to draw sort of log of z. Okay, and remember that log of z looks something like this. All right. So it's equal to 0 at 1. Okay, and what I'm sort of interested in, and I've probably not left enough space, but I'll tell you what, I'll zoom in. Okay, what we're interested in here is the change from 1 minus x divided by n. Right? Notice, if I look here, the height of this from here to here, alright, the change from here to here is really log of 1 minus x minus n minus log of 1. Okay, that's sort of this height here. And then the change in this direction, okay, is really minus x divided by n. So when I divide this by this, I'm really looking at kind of the slope of this line. I did that with a different colour. Alright. So if you think about it, what's inside this bracket here is really the slope of this line. Right? And as I let that n get larger and larger, what we're doing is essentially looking at slopes getting closer and closer to 1 until eventually we're going to end up with the slope of the logarithm at 1. Okay? So essentially what I'm doing is I'm kind of taking the derivative of this logarithm at z equals 1. Okay? So what I'm saying here is that the logarithm from this picture of 1 minus x divided by n minus logarithm of 1 divided by x over x minus n is going to get closer and closer as n gets to infinity of the derivative of log of z dz, but evaluated at z equals 1. Okay? We know that what that is. Remember that the logarithm, the derivative of the log of z, you should know is equal to 1 divided by z. So if I evaluate this at z equals 1, I'm just going to get 1. Okay? Okay. Right, so we're nearly there. So what I'm saying is, if I look at my expression here, and I let n go to infinity, okay, so looking at this expression here, and letting n get larger and larger and larger, what's going to happen to this guy? Well, it's going to give me the exponential of e to the minus x times what happens to this term in the square brackets here, which it goes to 1. So what I'm left with is e to the minus x, right? That's quite an important little lemma that crops up in all sorts of places, okay? Remember when we had our kind of birthday problem, where we had the football players, and we asked what's the probability that if we ask 23 players what their birthdays are, and we found it's about 50-50 chance that there are 2 players that have the same birthday. Well, sort of what was happening here is we were multiplying terms like this, sort of 1 divided by something to the divided by 365, okay, and we're doing that an order of magnitude which was sort of sufficient that we get some reasonable probability out as well, right? So we sort of went from 1 over 365, so 23 divided by 365, and doing that to about the power of 23, okay? The 23 times 23 is sort of the order of magnitude of the number of days in the year, okay? And so for that reason we've got some sort of moderate answer out, okay? So what this sort of fact is why that sort of that sort of seeming paradox was coming out, okay? Right, anyway, so that basically completes this last bit of the argument that this is true. Alright, so that's where this e to the minus lambda comes up in this expression here as well. Okay, though, you know, the calculation here isn't really a piece of probability, but a useful trick nonetheless. Okay, that's probably enough on the Poisson distribution for now. I might do a few more examples in a separate video, but that's probably enough for this one.